We had left off when we were getting ready to differentiate y equals sine of x times tangent of x. Because we're multiplying the sine and tangent together, that means that we're going to have to use the product rule. Before I get going on the product rule, I'm just going to jot down the derivatives that I'm going to need for that, so when I go to put it all together, they're ready to go. The derivative of sine is cosine, and the derivative of tangent is secant squared x. So now when I go to do the product rule, the derivative, dy dx, is we keep the first one, take the derivative of the second, so multiply by secant squared x, plus now the derivative of the first one, and then we keep the second one. Next, we're going to go through and rewrite everything in terms of sine and cosine to see if anything will simplify. Secant squared would be 1 over cosine squared, and tangent is sine over cosine. Well, by looking at this, I can simplify, cancel there. I can rearrange this a little bit if I want, and so I can either leave it like this and have sine secant squared plus sine. You know what? I think the best option here is, since I have a sine in both of them, I'm going to factor that out as my GCF. All right, I think that's my best option right now. So if I factor that out, I have sine of x times 1 over cosine squared is secant squared plus 1. Well, that looks pretty similar to one of my Pythagorean identities, so let me go check. When I look up here, I have tangent squared x plus 1 equals secant squared x. Well, if I wanted to move the 1 over with the secant squared x, I would have secant squared x minus 1. So since I'm given a plus 1, there really isn't anything I can do. My best option is to leave it like this where it's factored. That way, if I have to set it equal to 0 later and solve, I'm ready to go. Next, we have to find the second derivative of f of x equals secant of x. Well, the first derivative, not so bad at all. It's just secant of x, tangent of x. The second derivative is going to require us to do the product rule, because now we have secant times tangent. So for the second derivative, I'm going to keep the secant. The derivative of tangent is secant squared x plus, now the derivative of secant is secant x times tangent of x, and then I keep the tangent of x. Looking at this, I have a secant as part of each of the two terms, so I can factor that out. So f double prime of x is secant of x times secant squared x, plus I have tangent times tangent, so that would be tangent squared x. Maybe this is a Pythagorean identity. So when I go back up here and look again, tangent squared x plus 1 equals secant squared x. If I want to move the tangent squared to the other side to be with the secant squared, it would be secant squared x minus tangent squared x. Well, I have a plus, so that means that this is all I can really do with this problem. From here, we're going to jump to the last page because I believe we have completed all of the other problems. Oh, I found a page we skipped, page 6. We're finding second derivatives, that's why we skipped it. These had gotten a little bit redundant, but just in case. The first derivative, 8 times 6 is 48, x to the 5th minus 50x to the 4th plus 15x squared. For the second derivative, I'm not going to be able to do that one quite as fast because I'm going to need a little bit of calculator help to do 48 times 5. Which is 240. X to the 4th minus 50 times 4 is 200. X to the 3rd plus 30x. And there's our second derivative. For b, we have f prime of x. The derivative of x is 1. Bring down the negative 2, so that would be negative 64x to the negative third. For the second derivative, the derivative of 1 is 0. 64 times 3 gives us 192, x to the negative fourth. We could leave it like that because they started with a negative exponent, or we could rewrite it as 192 over x to the fourth. For C, you're like, oh, look, it's a quotient rule. No, you don't have to do a quotient rule. Because the denominator is a monomial, we can break this up into 3 separate pieces and then take the derivative of each of the 3 pieces. So that would be x squared over x, which is x. 2x over x would be 2. Negative 1 over x we could rewrite as negative x to the negative first. So we've rewritten the function. If I want to take the derivative of x is 1, the derivative of 2 is 0, the derivative of negative x to the negative first, negative 1 times negative 1 would be positive 1, x to the negative second. For the second derivative, 1 and 0 would combine and give us 1. The derivative of 1 would be 0, so now all that's gone. Bring down the negative 2, x, subtract 1 from the exponent. We could either write that, but the better option in this case, since we started with a fraction, is to end with negative 2 over x to the third. For A, we want to find the higher order derivative. So it tells us we want to find the third derivative, but we're already starting at the second derivative. So we only need to do the derivative once because we're almost already there. I'm going to rewrite this as the second derivative is 2 minus 2x to the negative first. Now, the derivative of 2, oops, my third derivative, 3 little hash marks. The derivative of 2 is 0. Bring down the negative 1, so negative 2 times negative 1 is a positive 2. X negative 1 minus 1 is negative 2. So this would be f triple prime of x equals 2 over x squared. For B, we're starting at the fourth derivative, and we need to go to the sixth derivative. So the fifth derivative of x would be 2, and the sixth derivative would be 0. That was quick and easy. An automobile's velocity starting from rest is v of t equals 100t over 2t plus 15, where v is measured in feet per second. Find the acceleration at 5, 10, and 20 seconds. Well, I guess it's a good thing we had skipped this one before because we need the quotient rule for it, and when we were doing these notes, we hadn't done the quotient rule at this point. The reason that we know we need the quotient rule is because we have a binomial in the denominator. We can only break it up into separate fractions if the denominator is a monomial. So since it's not, we're going to have to do the quotient rule. So the derivative of velocity is acceleration. The quotient rule is low d high, so low means the bottom. So 2t plus 15. D high means the derivative of the top, minus high, so the top, d low, the derivative of the bottom, over the square of what's below. So that means we square the denominator. I need to clean this up a little bit so I can plug some other stuff in later. If I want, I have a 100 that I can factor out. I don't know if this is going to make things better or not. We'll find out as we go. But because I have that 100, I can factor it out. When I factor it out, we're left with 2t plus 15 minus 2t. 2t plus 15 squared. 2t minus 2t, those cancel. So now I just have 100 times 15. that's not so bad at all. So A of t equals 1500 over 2t plus 15 quantity squared. So now we need to find the acceleration at 5, 10, and 20 seconds. So that means that we're going to just substitute in 5, 10, and 20. So we get 1,500 over, when I plug in 5, 2 times 5 is 10. 10 plus 15 would be 25 squared. If I put that in the calculator, that would be 1500 divided by 625, because that's what 25 squared is, which is 2.4. Velocity is feet per second, so this is feet per second squared. Now for the acceleration at 10 seconds, 1,500 over 2 times 10 is 20. 20 plus 15 is 35. So that would be 35 squared is 1,500 over 1,225. 1,500 divided by 1,225 gives me 1.22 feet per second squared. And the third one is at 20 seconds. So A of 20 would be 1,500 over 2 times 20 is 40. 40 plus 15 is 55. If I square 55, I get 3,025. So it would be 1,500 over 3025. When I put that in the calculator, I get 0.496 feet per second squared. Oh, sorry. Yeah, it's feet per second squared. All right, so there's my 3 sig figs. And then if I check again, now all of the pages look complete except for the last one, so we'll jump to the last page. For this problem, we are asked to consider the function f of x equals x squared times e to the 3x, and we're asked to find f prime of x. As we look at this, I have the product rule at play here because it's x squared times e to the 3x. So what I'm going to do is I'm going to jot down my derivatives so when I go to put them into the product rule, I already have them, so I don't really have to think about them later. So the derivative of x squared is 2x. The derivative of e to the 3x is e to the 3x times the derivative of the exponent, which is just 3. Cleaning that up just a little bit, we get 3e to the 3x. Now, when I go to put it into the product rule, I know that f prime of x is we keep the first, multiply by the derivative of the second, so that would be the 3e to the 3x, plus the derivative of the first is the 2x times the second, which is the e to the 3x. To clean this up, I'm going to look for a GCF. So I see I have an x in each of the terms, and I also have an e to the 3x in each of the terms. So that's my GCF. So my derivative is going to be x e to the 3x times, if I factor out an x from the first term, I'll be left with an x from the x squared and the 3. So that'll be 3x plus, and in the back, I'm left with just a 2. The graph of f has a horizontal tangent line at x equals 0 and x equals a. Find a. So we have already factored our equation. The horizontal tangent line is when we have a slope of 0. So if I were to take each of my factors and set them equal to 0 and solve, that would give me the locations of the horizontal tangent line. So the first term, xe to the 3x, that's the one that results in the 0. Because if I did xe to the 3x equals 0, x is going to be 0. So that's where the 0 comes from. So the a comes from the second one. So 3x plus 2 equals 0. 3x equals negative 2. So x equals negative 2/3. So that is where we have a horizontal tangent line. Let L be the tangent to the curve y equals xe to the 2x at the point 1e squared. Find the coordinates of the point where L meets the x-axis. So we have to find the equation of the line, and then once we find the equation of the line, if we want the line to touch the x-axis, that means that y equals 0, and so we set the line equal to 0 and solve for x. In order to find the line, the first thing we have to do is find the slope of the line. To find the slope of the line, we take the derivative. Whew, okay, here we go. Y equals, or dy dx, since we're doing the derivative. For the product rule, I'll keep the x, multiply by the derivative of the second term, which is e to the 2x times 2, plus the derivative of x is 1, and then we keep the e to the 2x for the back. I'm going to clean this up a little bit. Dy dx equals e to the 2x times, so if I factor out the e to the 2x, I'm left with 2x plus 1. So that's the equation that gives me the slope. I need the slope at the x coordinate of 1. So when x is 1, that means that the slope will be e squared times 2 plus 1, which would give me 3e squared. So that's my slope. Now I have a slope and a point, so I can set my slope and point into point slope form and find the equation of the line. So y minus y1 equals m times x minus x1, that's point slope. Y minus my y coordinate is e squared equals my slope is 3e squared times x minus 1, because my x coordinate is 1. When I distribute the e squared, I get y minus e squared equals 3e squared x minus 3e squared. I add e squared to both sides. So that means y is equal to 3e squared x minus 2e squared. So now we want to know where that line meets the x-axis. So to find out where this meets the x-axis, I'm going to set it equal to 0. Now I'm going to, that should be a 2. Now I'm going to solve for x, so I will add the 2e squared to the other side. So 2e squared equals 3e squared x. Divide by 3e squared. When I do, the e squareds cancel, so x equals 2/3, and they want the coordinates, so the coordinates would be 2/3, 0. Who knew it would be such a nice number after all those crazy e's? All right. Consider two functions, f and g, and their derivatives f prime and g prime. The following table shows the values for the two functions and their derivatives at x equals 1, 2, and 3. Given that h of x equals g of f of x and k of x equals f of x divided by g of x, find h prime of 2 and k prime of 1. So another way to rewrite h of x would be g of f of x. So that is what we use the chain rule for. So if we go back in our notes, back, chain rule. So the chain rule is f prime of g of x. So h prime of x is going to be, let's just double check and make sure we have the right letters in the right order. So, oh, notice it's f of g of x here. So if it's f of g, it's f prime. Keep the g, then g prime. So for us, since the g is the outside function, we're going to do g prime at f of x, and then multiply that by f prime of x. Okay, so that's the formula we're going to need. So to do this, f of x, we're finding h prime of 2. So h prime of 2 would be g prime of f of 2 times f prime of 2. So h prime of 2 is g prime of f of 2. So regular f of 2 is 1 times f prime of 2. F prime of 2 is 4. So h prime of 2 is g prime of 1. So g prime of 1 is 4 times 4, which is 16. For k prime is the quotient rule. I'm going to add myself another page here really quickly. Sorry, I ran out of pages. Insert new pages. Okay, so now I have more room to write. So if it's k prime, remember it's low d high. So regular g of x. D high means f prime of x minus high f of x d low over the square of what's below. So that's our formula. Now we're doing k prime of 1. So k prime of 1 would be g of 1 times f prime of 1 minus f of 1 g prime of 1 over g of 1 squared. Now I just have to go back to the table and get those numbers and then plug them in, multiply and divide. We're all done. So k prime of 1, g of 1 is 2 times f prime of 1 is 1 minus f of 1 is 3. G prime of 1 is 4 over g of 1 squared. So g of 1 would be 2 squared. 2 times 1 is 2 minus 12 over 4. So that means that k prime of 1 is negative 10 fourths. So k prime of 1 is negative 5 halves. And we are all set.